Hello, this is Math 2231 coming to you from the College of DuPage for summer 2020, and this lecture is the conclusion of continuity. When I left you, you were working on this, and some of you probably finished. I hope maybe everyone did, but let me give you a chance. You know what to do? Let's see how you did. Okay, well, the domain of this function is the closed interval minus 1 to 1, and it is continuous from the right and continuous from the left at the endpoints, so it's continuous on the closed interval. It is the upper half of the circle. Continuity is a well-behaved characteristic of functions. For example, if you have continuous functions, you can take a scalar multiple and still be continuous. You can add and subtract continuous functions. You can take the product and you can take the quotient. So many types of functions are continuous at every point in their domains. That doesn't mean necessarily they're continuous for all real numbers, but in their domains they are. So polynomials are continuous for all real numbers. Rational functions are continuous except where the denominator is equal to 0, and then they're not continuous. The nth root, it really depends on if n is even or odd, and we usually are going to be talking about real valued functions. Trig functions, the sine and cosine are continuous for all real numbers. The rest of these do have places where they are not defined, but they're continuous within their domain. And you can even compose continuous functions, and the answer is still a continuous function. Here's a problem for you to describe the intervals on the real number line on which each function is continuous. You have A, B, and C. You know what to do. Let's see how you do. Okay, the tangent function goes up to infinity. It has these vertical asymptotes. So it's undefined at these points, and there are an infinite number of these because n could be any integer, but these are the places where it is defined, is the open intervals between those. Now, because y equal 1 over x is continuous except at 0, and the sine function is continuous at all values of x, it follows that this is continuous at all real values except x equal to 0. It's the composition of the functions like we just talked about. But we have learned that the limit as x tends to 0 does not exist. That means it can't be equal to 0. That means it's not continuous at 0. So these are the intervals on which it is continuous, but it's not continuous at 0. This function is similar, except you see the sine of 1 over x is between 1 and minus 1. So if I multiply all the way through by x, I have it bounded by these functions. We did an example like this, and so what happens is this forces it to go to 0 at 0 because of the x there. So this is continuous for all real numbers. This is what the intermediate value theorem says. If f is a continuous function on a closed interval AB, and k is any number between f of a and f of b, then there's at least one number c in AB such that f of c equal k. You have to think about what that means, but it tells you that there exists at least one number, and it also tells you that a continuous function takes on all values between if x takes on all values between a and b, then f of x takes on all values between f of a and f of b. This is a very useful theorem, and sometimes we have problems, perhaps there was one assigned, where you have to find the value of c. It doesn't tell you how to find it, it just tells you whether one exists or not. The intermediate value theorem guarantees the existence of at least one number c, but there might be more than one number c, and sometimes there's just one. And of course, you don't have to take on every value between f of a and f of b if the function is not continuous, because we have continuity in the if part of the theorem. Here's an application of the intermediate value theorem, though. Use the intermediate value theorem to show that the polynomial function, which is continuous has to have a 0 in the interval 0 to 1. You don't have to find it, it just said prove that there was one. Well, you see, this is a continuous function on a closed interval, so it does satisfy the intermediate value theorem. That means it takes on every value between f at at 0, it's negative here, and it's positive on the other end. So it takes on every value between them, and that means it crosses the axis because there's some value at which it crosses 0, because 0 is between -1 and 2. The bisection method for approximating the real zeros of a continuous function is similar to the method talked about in example 8. If you know that a 0 exists in the closed interval AB, the 0 must be in one of the half intervals, and by the signs you can determine which interval contains the 0, and by repeatedly bisecting the interval you can close in on the 0 of the function. This is exactly what your calculator does. If you're trying to find where this hits the axis, it will ask you what is a left bound. You will pick something that is negative. It will ask you what is a right bound. You will pick something that is positive. It knows there's a root in between. It goes through the calculation and eventually renders you an approximation to the 0. Here's some true-false questions to maybe test your understanding of this. There are 4 of these. You know what to do? Let's see how you did. Should be true, true, false, false. And these are the reasons. Number 100 is true, but realizing it could be both. And I think these are pretty self-explanatory. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless.